question too.
Yeah.
Can I bring this possibly tomorrow?
Yeah, you can bring models.
Really?
Yeah.
Okay, cool.
Yeah, just like on exam 1, models are fair game to bring, if that helps you out. So definitely feel comfortable doing that. So exam tomorrow. So just a little bit of info. So of course it is written, just like last time, I write big structures, and so I basically, it's going to be 6 pages again, but the structures are huge. I mean, so you end up, that gives us, and honestly what I think I'll do is I'm happy to give us everyone up to 55 minutes or so. I'm going to have to call time eventually, but that gives you like 9 minutes a page, and really they aren't pages that you should have to spend more than 9 minutes on. So hopefully, don't be intimidated again by the length. It's just going to, they're big structures. I like to err on the side of bigger structures than smaller structures. Gives you more space to draw as well. So anyone have any questions to start out? Yeah. And let's just start out actually just with general questions, if there are any of those. Yeah. So like an acyclic, just like, we'll take a look at some examples like that for sure. Yeah, Sarah, do you have a question?
Yeah. When do we draw which hydrogens on the products? Because sometimes you might, sometimes when you're doing a reaction mechanism, it involves adding a hydrogen, so you have to then show the other hydrogen that was already attached.
Yeah.
But then when you're drawing the ultimate product and you have 2 hydrogens on the carbon, do you draw them both?
Yeah, so the question was, when do we draw all the hydrogens in on products? Because there's some reactions where we're actually hydrogens, and so do we need to add those or show those specifically in the product? And so I know sapling is a stickler about that. So if you have a CH2 in sapling, it'll give you credit if you draw no hydrogens because they're implied. It will give you credit if you draw 2 hydrogens because they're explicit, but it wouldn't give you credit if you only drew 1. And so, honestly, if there were 2 hydrogens and you showed 1, that's fine, because if you don't have it charged, I know there must be another hydrogen there anyway, right? So I'm always going to assume that there are hydrogens there if you draw a carbon with only 3 things connected to it and it's a totally neutral carbon. So don't worry too much about that. Now, where you will need to make sure you draw that hydrogen in is if we add it and we form a stereocenter, right? And so now it matters that we're adding to one side versus the other. So in those cases, you'll have to make sure that you do show both of the hydrogens. But if it's a CH2, I don't really care, as long as you have it shown charged, uncharged.
For the H2 with a metal, the
Yeah.
last reaction,
Yeah.
if we have that just adding to a non-substituted cycloalkene, can we show just the 2 hydrogens that add? Is that
That's fine, as long as you're showing the charge and the carbon uncharged, because I'm going to know what you mean. Okay, really quick, this won't take very long. So last time I said that Sadie could come to the workshop, and she got sick, right, because she ate like an entire French loaf. So. make up for that last time. Now everyone has had a chance if you came to workshop to see Sadie. Round of applause for Sadie. All right, we'll do some chemistry now.
Can we draw all the hydrogens if it helps us?
Say it again.
Can we draw all the hydrogens if it helps us?
Yeah, absolutely. So you can if you want to draw hydrogens, you can always draw hydrogens in. It's never incorrect to draw hydrogens because they are in fact there. Yeah, they're always there. Yeah.
Would you be willing to run like a generic analysis reaction?
We'll do that. We'll do it in a little bit. I just want to get maybe just general questions about like exam formatting type stuff. Yeah, Chris.
So there's been the ones where we have to draw the starting material and it's like an alkene. Is it okay if we draw it like 180 degrees upside down of what like an answer key
You
says?
can draw a molecule in literally any orientation because it doesn't matter where, if there's a molecule and let's say it's this projector, we can look at this thing from a lot of different perspectives, but we're never changing anything about the projector, right? So, if you want to draw my hand and you draw it like this, or you draw it like that, it's still my right hand, right? The stereochemistry is not going to change no matter how we rotate my hand. So you can definitely orient your molecule any way that you want to.
Okay, thank you.
Are we going to have to know like the full step-by-step mechanisms of all the reactions, or if we just produce a product?
So it's definitely, and so I'll go ahead and say it wouldn't be an organic exam if there wasn't one mechanism problem where I said, here's a starting material, here's a product, show me all of the intermediates and how the electrons move using arrow pushing. So I can guarantee you there will be a mechanism. Fortunately, that's why I really tried to highlight the fact that ultimately there's really just three types of mechanisms, right? One that goes through a carbocation, one that goes through a polonium, and then the concerted mechanism. So it's got to be one of those three. So as long as you have a good idea of what's going on with those three, it shouldn't be too bad of a problem drawing three mechanisms. Yeah, Gabby?
Well, you have a question on the exam that asks us to do the reverse reaction, so the dehydration of a molecule on the practice.
Right, and so you're asking about that mechanism that was on the practice exam where they'd had you draw basically the backwards reaction. I wouldn't put that on an exam. Again, those aren't my practice exams. So, yeah.
When we're asked to give the products, if there's a reaction that has more than one, or not the product, if you want us to show the reagent and there's more than one possible reagent, we just pick one?
Yeah, absolutely. There's always going to be cases. In fact, most chemical transformations, there's usually multiple reagents that you can use to undergo that process. And so, yeah, as long as you chose one that would get you the product, that's absolutely fine. There's a lot of right answers in reality when we talk about chemical transformations. So, yeah, hope.
Are you going to ask us to do something just by name? So will you say do an ozanolysis reaction, or because some of them we don't have names. The seventh one we did, I don't have a name for that one. It's the one with osmium.
Yep, and so that one, you can just call an osmium tetroxide diol reaction. I'm not going to, more likely instead of giving you the name of a reaction and expecting you to show me what the material, the starting material of the product would be, more likely I'd show you the actual reagents written out. Yeah. So definitely focus in on the reagents themselves. Any other, yeah, Sarah?
So a lot of the problems we've had have been where we're given two of the three, either reactants, products, or reagents, and we have to give the one that's missing. Would we ever have to give two of the three? Would you ever give us just a product to show me the reactant and the reagent?
I won't say whether or not that's on the exam, but I would say, it would be fair, right? Because if I showed you a diol product, how many ways have we learned to form a diol from any starting material? We've just learned one way, right? And so there's only one thing you've learned that could form that product. You know it's an osmium tetroxide reaction, and you know it has to be an alkene. So it would be fair, but I don't necessarily have it on the exam.
If you give us a question where we're given a product, does it matter to give the reagent of is there two different reagents, whether they're a carbocation or a hydrogen? Because we have one that's navigation and LH, and there's both carbocation.
So we've learned that specifically when we're forming an alcohol, we know that if we're doing an acid-catalyzed hydration, we know the stereochemical implications are that a lot of products can form, right? We've also seen that if we do say a hydroboration, it's an anti-Markovnikov spin addition, right? Because it goes through a concerted mechanism. And so certainly what I could do is I could show you a diol with a specific regio or stereochemistry, and so we've only learned one way to maybe do that specific alcohol, right? Based on the selectivity of the reaction. So in that case, you can't do an anti-Markovnikov addition of water to form an alcohol using acid catalyzed hydration. So in that case, the acid catalyzed hydration wouldn't be acceptable because it would lead to a different product. Yeah.
Asking for the house parent for kids. For the problems where you ask for products, in some cases, so for like 16, those practice problems, in some cases you have them just drawn on lines when there's three constituent groups, but sometimes there are wedges and dashes. In which case do you prefer which?
So the only time that you'll really see no line, or at least not a wedge and a dash when showing stereochemical information, are these big structures where we have lots of rings fused together. And the reason is, if we show things on on wedges and dashes, the picture gets really confusing really quickly. There won't be anything on the exam in terms of fused rings such that we can't show a wedge and a dash for every stereo center.
Okay, so in general we should draw wedges and dashes.
Absolutely. Yep. And as long as it's a stereo center. Right, if it's not a stereo center and there's no chirality at the carbon, then there's no need because it doesn't really mean anything. Yeah. All right, so I am yours for 2 hours. Let her rip. Yeah. Yep. All right, so we're going to do ozonology. You want cyclic or acyclic? Acyclic? All right, so we're going to do an acyclic ozonolysis example. Let's see, this will be workshop 13. All right, so let's see. What we could have is we could have a structure that looks, say, like this. All right, we'll use that. So now we've got an acyclic alkene, right? We do have a cyclic part of this, but it's just a substituent. There's no alkene, so it's actually not a cyclic alkene in this case. All right, so we want to hit this with ozonolysis. And so what kind of workup do we want to do? Reductive, or I'm just going to say oxidative. So we'll do an oxidative workup, H2O2. That's the trickier one, right? Because something changes. In the reductive workup, we just keep it the same. So we'll do the fancier one. And so in this case, we can go ahead and determine the product. So what's ozonolysis all about? Cleavage, right? So what I like to do is just squiggle through that double line, and so basically we're going to separate these things apart and end up with two products. And so what we'll do is for the first product on the left, nothing changes in our cyclobutane ring. So then we end up with a carbon there. Now, at this carbon, there was once an alkene, right? And so what's that now converted to? It's still a double bond, right? But it's just we converted it into a carbonyl. And so that CC double bond more or less turns into a CO double bond. And so at this position right here, did we have a hydrogen?
Yeah.
Yeah, we definitely had a hydrogen, but since we've done an oxidative workup, what does that get converted to? OH. Yeah, that now gets converted to an OH. And so we end up with that as one of the products. And then we pretty much do the other side. So the other side looks like this. And so what do we need to draw here? Yeah, we need to show keep a double bond, but now it's CO double bond, right? And so we've cleaved it. The alkene has become a couple of CO double bonds. Are we going to end up with any oxidation going on here? No. No, right? Because this is a methyl group and this is a methyl group. And so we don't have any hydrogens directly attached to the alkene. And so this would basically be our products right here. Yep, and so in terms of mechanism, we learned basically just the first step of ozonolysis, right? And so how we can draw this, let's see. And so honestly, in a lot of these you know, it's a lot easier to draw the mechanism with cyclic products because it's easier to show the stereochemistry. And that's why I use cyclic products so much, is because it's easier that way. So if we were to do a mechanism here, let's see what we could do. We'll start with our double bond like this, and so we're going to have ozone. Which looks like that. All right, so let's make sure we're in it correctly. All right, so there's our ozone, O3. Okay, so what's the first step of our mechanism? And this is, you know, I've harped on this a ton. What is always the first step of a mechanism in electrophilic addition? Where's the first arrow come from? Start with the pi bond, no matter what you do. And so we know, we said in class that when we form our intermediate in ozonolysis, we basically form a new 5-membered ring, right? We have the 2 carbons involved in the alkene, and then the 3 oxygens for the ozone, and they just form a new 5-membered ring. And so the way that we can push arrows is we'll just show going, and a way to remember this is we're always going to draw our arrow to the oxygen with the double bond, right? And so that's maybe just an easy way to remember that. And so of course we need to break the pi bond because otherwise we'd break the octet rule. And so what's the third arrow that we're missing? Where do we start it? Yeah, we start with a lone pair on the oxygen and basically draw that right back in to our carbon there. And so what we'd end up with, of course, is this which kind of mechanism is this? Is it concerted? True or false? True. Okay, so if it's a concerted mechanism, is it syn or anti? Syn. So what we'll want to make sure to do is show that we're adding on the same side. And so I think the easiest way to maybe show that is you go ahead and draw part of your carbon chain. So we'll call this our carbon chain, right? And so if we're going to add our ozone from the front, well, we're going to end up with that on a wedge and that on a wedge, right? And so ultimately we have a structure that looks like that. We need to show them both on wedges. And so what's happened to our methyl group that we haven't drawn in yet? It's been pushed back, right? It's now on a dash. And so we could show it like that right there. This would be, let's see, this would be plus enantiomer or plus diastereomer? I mean, so do we have any chiral centers that we didn't just form? No, we just have those 2 chiral centers, so that should be plus enantiomer, because this is not a chiral center because of the symmetric ring that it's attached to. So this would be plus enantiomer. And this is it. This is all you need to know for ozonolysis. I'm unlikely to ask for an arrow pushing mechanism for ozonolysis, but I can promise you that maybe you need to be able to recognize products and starting materials from ozonolysis itself. So, yeah.
When would it be a situation where it's plus diastereomer?
So an example where it would be plus diastereomer is, let's say our starting material was now this, where we already have a chiral center. And so now, when we do our addition of our 5-membered ring, this chiral center won't change, but everything else will look the same, right? So we could add from the front face. And so we had a structure like that, and so...
So when something isn't changing.
Yeah, basically, so if you already have a chiral center, you're going to end up with plus diastereomer. If you don't have a chiral center, then you'll have plus enantiomer.
Okay.
Yeah, and I think that's a pretty good general rule. We could write that down. So let's say achiral starting material leads to plus enantiomer. Chiral starting material leads to plus diastereomer. And I think in the vast majority of cases that'll be true. So. Yep.
Where do the arrows get pushed in the intermediate products to H2O2 to form?
And so we didn't learn that. That mechanism we'll just call it a little too complex for Chem 206. So we just wanted to see that sure enough, this first step is concerted, and so it truly is. It adds in a syn fashion. I've had a few questions where on one of the practice exams, it was asked, all right, so if you see this reaction, is this going to be a syn or anti-reaction, or is it none, right? We have three options in terms of stereochemistry. Now, what we've been doing in class is I've been basing it off of the product, right? So we look at this product, or at least the product that would result, it's a couple of carbonyls. Does the product have a chiral center in it? No, we don't have any stereochemistry in the product, and so we've just been saying none. There's no stereochemistry. But if we're talking about the mechanism, would we consider this syn or anti? It's syn, right, just because it's going to a concerted mechanism. But I'm clear about that on the exam. There's not going to be any gray area. Are we talking about mechanism or are we talking about product? So don't worry about that. I know some people were confused why the practice exam looked a little different from what we would expect.
Similarly, can we go over a full arithmetic for a halogenation reaction?
Yeah, are there any other questions about these ozonolysis? Let's work on that for just a few more minutes. Madison.
Can we not keep going with like the workup step to potentially like break the free oxygen?
So really, there's only two things that I can ask you. It can either be this top one where I can say, all right, what are the products giving the starting material, or what would the starting material be based on these products? So that's a question I could ask. Or I could say, I guess, draw the mechanism for ozonolysis. But again, this is pretty much all we've learned in terms of mechanism of ozonolysis. So I wouldn't, it's unlikely that I would ask that on exams. It's relatively straightforward. Yeah.
How is the starting material for this achiral?
So while we do have EZ stereochemistry, or do we? I mean, I guess we don't even have EZ stereochemistry because we have a couple of method groups off of one end. So we don't have a chiral center, basically, in this. So if you try, the question you can always ask yourself if you see, if you're asked, is it chiral? What's the question I've told you to ask yourself? Does it have an enantiomer? And so does that starting material have an enantiomer?
Yeah.
Yes or no? It doesn't, right? Because we don't have a chiral center in the first place. So what we've got is an achiral starting material. What about this one? Does this have an enantiomer? Sure, right? Because here we've got a chiral center. And so here we've got a chiral starting material that leads to this plus diastereomer. Here we have an achiral starting material that leads to this plus enantiomer.
But I thought that achiral meant that it was like completely symmetrical and superimposable.
So, yep, and that's what we've got right here. So let's prove that. So maybe it's the most straightforward way to see this is we can take that starting material. And so if we want to, the first way we learned how to draw an enantiomer is we said, all right, we'll just take the mirror image of it. And so left and right change places, right? So what we would end up with is a structure that looks like this. And so are those the same structure? Yeah, those are definitely the same structure. So what we're seeing is that this material has no enantiomer because, in fact, these are two overlappable structures, right? We can superimpose these two structures. And so since there is no enantiomer, what we have is an achiral starting material.
Okay.
Yep.
Would you be willing to do osmosis reduction with cyclic alkene?
Yeah, so for a cyclic alkene, we could have, say, let's do an interesting one. How about, all right, so we'll do a cyclopropene ring. All right, we haven't seen something like that. And so again, ozonolysis is all about what? All about cleavage. Now this is a cyclic alkene, and so how many products are we going to end up with? One, right? Because while we cut this thing in half right here, it's still connected through this carbon right there. So we're going to end up with just one product, and so it's all about cleavage. So go ahead and draw a squiggly line through your alkene. You know that's going to break. And so what we can do is just redraw our structure without that double bond. And if it helps, we can number carbons. So we can say we've got 1, 2, 3, 4. And so we add that this is going to be a reductive workup. So we've got ozone. And then what's our compound we use for the reductive workup? It's dimethyl sulfide. And so we've got carbons 1, 2, 3. So everyone see how we got from these carbons to these carbons? We basically just cut the connection between 1 and 3. And so we know that each carbon 1 and carbon 3 were both double bonded in that alkene, and so we just want to show that and that. So this is an implied hydrogen, and it doesn't change at all. It stays the same. Yeah?
So on the practice test, the answers were like the double bonded oxygens above and below. What is that?
So that's just a different perspective on the same molecule. You know, we could draw it like this. I could draw this compound. Let's see. I could draw it like this. That's the same thing, right? If there's no, and especially in these these achiral products, you know, you don't even have to worry about stereochemistry as long as you have the connectivity.
So we should show the implied hydrogen if we have something like this in the test?
So you could show it or you could not show it. As long as you've, you know, if you didn't show it, like we're doing right here, well, you're not showing a charge here, right? So what that tells me is that you're implying that there must be a hydrogen there. Because if there wasn't, this would have to be a charged carbon. So, yeah, that would be fine. Yeah, Lydia?
Can you draw it not in a parallel way? Because I know one of the examples,
What did you say?
one of the examples we did in class, when it was a cyclohexane, we didn't break it all the way down to a line. You leave it in the ring just with the bond.
Yeah, absolutely. I mean, and so that's kind of what I meant to do there. But yeah, that's maybe the easiest, straightforward way to do this is just redraw the same exact structure you've got. So that would be, all right. So ignoring the alkene bond, right? So we've copied that down, right? And now just add in your CO bonds, and you're good, right? That's the same thing as that. Is the same thing as that. Those are all the same compounds. Yeah. All right. Last questions on those analysis. We spent a lot of time on it. We can come back later. All right. New questions.
Can we go over a Fisher projection?
We're not going to go over Fisher projections because they're not on the exam. I feel like I've said that a lot. Hopefully the word has gotten out by now that there are absolutely no Fisher projections on this. I hate them. They're the worst. Yeah.
It seemed like one was like rotated 16 and
Sure.
180.
Yeah.
So that's which one?
Okay, so I've got some questions about this, and that's why I spent time on class. Let's look at another one. So let's say that we've got, let me think about it for a sec. Let's do a material. All right, let's say we've got this product right here, and so we're going to ask ourselves, well, first off, do we have two stereostates? Sure. And really, I could just give you this, because how many ways have we learned to add a halogen and a water molecule to an alkene? One, right? It's the halohydrin reaction. So we know that mechanistically what must be going on is an addition of a halohydrin. We've learned two ways to do that. We could do it either through BrOH, or we could react with B2 and H2O. And so both of those mechanisms are in your notes. We've shown how to do the halohydrin reaction from either of those reagents. And so most importantly,
Do you mean BR2?
Yes, that wouldn't make much sense. Please never hesitate to, it is so easy to drop something like that in this class, so never hesitate to call me out. All right, so let's see. Most importantly, what we've got to think about, so we can't really talk about regiochemistry because we've got a secondary carbon and a secondary carbon, so there's nothing there. So what we do have to think about, though, is the stereoselectivity. And what is the stereoselectivity of a halohydrin reaction? What type mechanism is it? It's a halonium type mechanism, right? And so what is the stereoselectivity of all type 2 mechanisms? It's anti, right? All right, so we know it's anti, and that's really the big, key, important piece of information here. It's anti. So what we're going to do is we're going to take the two things that we've added, and so we know that that's the bromine and the hydroxyl group. And so how are we going to orient them? On the same side or on opposite sides? Definitely on opposite sides, right? Because directly after the addition of these two things, that's where they would be. They'd be on opposite sides. Here, we've had to go under some sort of bond rotation to get them where they're at, but we know right after addition they'd be anti. All right, so let's draw explicitly what we've got. We've got a hydrogen here, and we've got a hydrogen there. So that's the form of our stereocenter. So let's get these things anti. And so let's say, and we can do this any way we want to. Here's what I'm going to do. So I'm going to put my bromine in the plane and up, like that. All right, so what that means is we're going to have a wedge and dash up or down now. It's going to be down. And so if we rotate that bromine, let's think about where it is up here. It's pointed up, and it's kind of pointed back, right? And so how do I rotate that bromine to be in the plane now? I'll just rotate it forward, just a little bit like that, right? So it was back here, and so I'm rotating it now that it's straight up and in the plane. And so that hydrogen, or really it might be easier to think about the methyl. So here's my bromine, right? And here's my methyl straight down. And so if I rotate my bromine, the methyl is going to rotate in the same direction. And so is my methyl, which was straight down, going to be on a wedge or a dash now? It's on a dash now, right? It's pointed this way. So our methyl is going to be on a dash, and our hydrogen, it's still forward, it's just on a wedge. We haven't rotated a full 120. We've rotated, I guess, 60. Okay, so if our bromine's up, that means that we're going to want our hydroxyl group where? Down, right? We've got to orient it anti, and so that'll be there. All right, so if we rotate our hydroxyl group to the down position in the plane, we're still going to have, let's see, we'll have dashed thing and wedged thing. And so our methyl that's straight down, if we rotate it in the same direction, will it end up on the wedge or the dash? Yeah, I hear dash, right? And so that's exactly where it will end up. We're rotating it in the same direction. So those three things, they're going to all rotate together, either clockwise or counterclockwise, to go from here to here. All right, so if we rotate our hydroxyl group from the front to down, that means our methyl group is going to be pushed to the back and be on a dash, and that's exactly what we see. All right, so then we've got our hydrogen there. Okay, so to figure out what starting material would be able to give us this product, have we oriented the two things we've added anti? Yeah, we have. And so all we want to do now is we can just consider, that maybe the easiest thing to do is the bromine, just plug it off, and the hydroxyl group, just plug it off, okay? And so think about the double bond that would lead to that. All right, so we've got our methyl on a wedge there, on a dash, and we've got our methyl on a dash there. We've got our hydrogen on a wedge coming forward, and so hydrogen on the same side. And so if we draw this thing with 3D geometry, we'll just pretty much keep it oriented as it is. We've got our methyl back, and so we show that there. On the right side is the methyl dash or wedge?
Dash.
This dash, right? And so that stays where it is. Hydrogen and hydrogen are on the same side. All right, so now we'll go the other way just to kind of prove that this is what happens. But first off, is this E or Z? Yeah, this is the Z double bond, and so importantly, the Z double bond, the Z alkene is the only alkene that will lead to this product right here, not the E alkene. All right, so let's go through this mechanistically. What would it look like? So we'll use BrOH as our reactant. And so if we want to go basically from this picture to this picture, what we can do is we know that we'll start our mechanism drawing to the bromine. And so that kicks off the hydroxyl group. But being a type 2 mechanism, what also is going to happen? We're missing an arrow. Where's the arrow going to come from? From the bromine, right? Because it's a type 2 mechanism. We know we need to end up with a bromonium. And so we'll start with one of the lone pairs. And we'll add back in. And again, there's no regioselectivity, so it doesn't matter, which we draw the arrow back to. We'll end up with the same product in either case. And so in doing so, basically we're adding our bromine from the top face. So what does that do to the substituents? Pushes them down, right? And so mechanistically, we're going to go through an intermediate where we've added our bromine from the top face, and all the substituents have been pushed down. All right, so that's our intermediate. Now, we've already said that this type of addition is an anti-addition, right? And so that means when we get to our next intermediate, we've got OH. Is that going to add to the top face or the bottom face? It's going to add from the bottom face, because that's what anti is, right? It's got to come from 180 degrees of our carbon-bromine bond that we want to break. Knowing that we're getting to this picture right here, we already know which bond we have to break. We have to break that bond, right? I mean, we know where we're getting to. We know where we're going. And so that means that we have to form a new bond from our hydroxyl group from the back side of that bond. So that requires, because it's an anti, because we have anti-stereoselectivity, it requires that kind of addition. And so on the left side, these substituents, are they going to stay down or are they going to change? They're going to stay down, right? Because this bond doesn't change. The orientation of this carbon-bromine bond, it's still going to be up and in the plane. It might scoot out a little bit because it's no longer stuck in a three-membered ring, but it's still on the top side. But what about these two substituents? Are they going to stay in the same place or are they going to be pushed up? They're going to be pushed up, right? Because now we're adding something from the bottom. And so what we end up with, I guess it's just this picture right here, right? And so the stuff on the left side stays the same, but those methyl groups and the hydrogens, they get pushed up, and so they end up with this picture right here. Yeah?
Why did you have to draw the starting material so that the metals were perpendicular to the plane of the page? Why couldn't you just left it? Because the first product that you drew, it has the substituents anti. Couldn't you just pluck those off and left the metals in the plane of the page and drawn your Z starting material?
Are you saying these are anti?
Aren't they?
Yeah, why aren't they?
So, all right, so those aren't anti because we've got a bromine pointed up to the back, and then we've got a hydroxyl pointed up to the front. And so are these things anti to each other? Right, so this is our hydroxyl group up and on a wedge. This is our bromine up and on a dash. But anti things are 180 degrees from each other, right? They're like this. And so they're not actually anti in that orientation. We had to do a little bit of bond rotation to make them anti. And that's why in class I did that on a Newman projection, right? And so if you're confused with what you're seeing, go ahead and convert that to a Newman projection, and then it might be a little more obvious if they are anti or if they're in another conformation. It's a really good question. In the back?
How would it differ if it was CRQ H2O?
So the mechanism is a little bit different in that you end up with the same intermediate. All right, so you'll end up with this intermediate. And so now what we have in solution, we have the Br minus that resulted from cleavage of the bromine-bromine bond, and then we've got H2O. And so we've gone over this several times. Which is going to add, the bromine or the water? Why? There's a couple of reasons. So typically you're going to have a lot more water in there, right? And so if you have more of something, it's more likely to react. But which one is just simply more nucleophilic? It's just water. And so you're only pretty much going to see the water add in. So at this point, we would add our water into that position. But by using water instead of hydroxide, we're basically going to end up with an extra intermediate. And so what that will look like, and it's because we can't, our oxygen's already connected to two things, and that's not going to change while we're forming this red arrow bond right here that I'm showing. You get a question, Hope?
Yeah, is it saying something is more nucleophilic the same as saying it's more electronegative?
No.
Okay.
They might be a little related to each other, but they're definitely not going to be the same thing.
Okay.
Yeah. I would say instead of relating nucleophilicity to like polarity, I would say nucleophilicity is a lot more tied to basicity.
Okay.
So if something is basic, we know we're donating electrons, and then when something's acting as a nucleophile, it's also just donating electrons, right? So those are going to go pretty, still not perfectly, but pretty close to each other. All right, so we'll have OH, methyl dash, hydrogen wedge. So then how do we go from this intermediate to up here? Yeah, we have to deprotonate, right? We've got a positive charge here, and we're used to snapping something to the positive charge to get rid of it, but that's going to violate the octet rule in this case because we know we have an implied lone pair there. And so you can use B or H2O. We can just show B. And so we always have to make sure we do this last deprotonation step, basically, to get to a neutral product. And so in both cases, you end up with the same product. Slightly different mechanisms because one goes through this positively charged oxygen. Yeah?
So in that case, when you drew the reactant, you wouldn't have to do the wedges and dashes because it's not chiral centers, right?
Well, in this case, it is, right? Because we've got a carbon here connected to 4 different things and a carbon here connected to 4 different things.
Right, but for the reactant, you couldn't just draw them on lines.
Oh, yeah, you can draw these anyway. The reason that I typically draw that in the plane is just because it's easier to see that anti-relationship between the bromonium up here and then the incoming nucleophile on the bottom. I just think it's a lot easier to draw that on paper that way. Yep.
That last step, would you have to show the B, or could you just show the arrow at the 8?
Say that again?
Would you have to show the B arrow? Would you have to show the arrow coming off the B?
Yeah, you've got to show that deprotonation step. So anytime we're drawing out a mechanism, we have to show all electron movement involved in forming new bonds and breaking old bonds. And so since we know that if we're going to break this bond right here, the hydrogen has to be forming a bond with something, we do need to show this other arrow. So if you don't want to use B, we also know that there's a lot of water in there, and so you could also do the same thing using water. It's the same result in the end.
Then would you need to show that you have hydrogen at the end?
I'm not too much of a stickler about showing hydronium and HB+. I'm mainly interested in the organic product, so yeah, I don't care too much. So if we were to draw Newman projections, let's draw... All right, so first we'll draw this one. And so we look down that bond. So the Newman projection that we get, we've got methyl. What's up and to the right for that first carbon? It's a hydrogen, right? So we've got hydrogen, methyl, bromine on a wedge, so back. And then is this an eclipsed or staggered conformation? It's eclipsed, right? So that's how we draw it. We've got another methyl down in the back. So we'll show that methyl there. So what's at the top left, the hydroxyl group or the hydrogen? Hydrogen. That's the hydrogen. And so here is our hydroxyl group. And so now we can see truly the relationship between that bromine and that hydroxyl group. Are they anti? No, definitely not. And so what we've essentially done is, let's see, so down here, if we were to draw a Newman projection for this picture, what we've got is our bromine straight up, our hydroxyl group straight down, and so, let's see, that'll be hydrogen, methyl, and then right here we've got hydrogen, methyl, and so again, we've got methyls on the same side, hydrogens on the same side, and so that's also what the initial alkene must look like. We're going to have the Z alkene. So that's a closer look at why those things were anti in this picture right here. Questions about this? Of the Newman?
Yeah, so when you're turning that to the final drawing, how do you know if methyls are on the top or the
Doesn't matter. As long as it's the Z alkene, you've got the same molecule, just in a different perspective. All right, new questions. Sarah.
Can we go over number 9 on faculty exam?
Number 9.
The first one. On the 2014.
2014. All right, we're looking at 2014, number 9. Okay, so let's see. All right, so let's start out with the middle one. All right, I mean, it doesn't matter. We can start from the top going down. Okay, so at the top one, it's a little odd, right? Because we've added a hydroxyl group to a position that we didn't have the original alkene, right? So to maybe think about what could be going on. It looks like there's possibility for a shift there, right? People agree. So I think what we probably have is our first step. What is it? If we're going to do a shift, what kind of mechanism must it be? It must be a carbocation type mechanism. And so we'll just say some acid reacts. And so which will the proton go to that primary or the secondary carbon? It'll go to the primary. And so what that'll end up with is give us an electron-efficient secondary carbon. And so can you see anything that we might be able to shift to go from the secondary carbon to maybe a carbocation to maybe a more stable tertiary carbocation? Yeah, we could undergo a 1-2 shift like this, which would lead us to this carbocation. And so we should be able to go from that carbocation to this product by reacting it with water. So, of those 5 reactants, which would lead us basically into a mechanism where we could undergo that process? It'd be C, right? So it would be our acid catalyzed hydration. So we know that's going to be C. Would let's see, what else could give us alcohol? So we know hydroboration gives us an alcohol. Could we ever undergo a 1,2 hydride shift with hydroboration? No, it's a concerted mechanism. We don't go through a carbocation, so it couldn't be hydroboration. And then we've got oxymercuration. And so we know oxymercuration is a Markovnikov addition of water, but again, could we go through a 1,2 hydride shift in an oxymercuration reaction? No, it's a type 2 mechanism, right? We don't have a carbocation. So it's only going to be C here that we're going to go through a carbocation. Okay, so then what about for the second one? Would you classify this as, so again, we're adding water to it basically. Would you classify this as a Markovnikov or an anti-Markovnikov addition? It's definitely Markovnikov, and so we know that C gives us Markovnikov. Did any other ones give us a Markovnikov addition of water? Yeah, E would, right? And so oxymercuration also gives us Markovnikov addition, and so I see, let's make sure this is right. I see no reason why either wouldn't lead us to this product, right?
Wait, either one.
Yeah, so either C or, now certainly with C we might expect to see some other products, like resulting from a 1,2 shift, but both of those give Markovnikov addition of water, and so does anyone have an objection to using either? They should both give us the products there. Gabby?
For the carbocation reactions, would it also have to be like plus an anti or plus
Yeah, so in cases where we're forming two new chiral centers, certainly you could form 4 total stereoisomers, but I don't think there's any that I've put on the exam where there's more than these 2 possibilities. So, yeah. Yeah, because, for example, here we're adding the hydrogen, but we're adding it to this position, and so that's not a new stereocenter. We're really just forming 1 stereocenter there, and so it's just going to be that plus 1 other product. Yeah. All right, so then what about the bottom one? Yeah, so you should notice that we've added the hydroxyl group now to the primary carbon, and so that's an anti-Markovnikov addition, and we've only learned 1 of those. What is it? It's hydroboration, right? And so that must be hydroboration. There's really no other way we could get to that product. Yeah?
Are we looking to show like the energy diagrams other than the carbocation?
Yeah, so I just showed you energy diagrams for the addition of acid and then the acid catalyzed addition of water. So that's really, I think, the one diagram. Yeah.
If you ask us what the reactants were for the acid catalyzed, would you be chill with us just writing HA, or do we definitely need to put?
So it depends on the product. I mean, I guess if the product you've added a chloride, it must be HCl, right? But and especially mechanistically, I'm pretty happy usually going with generic things but you must always show the correct intermediates and correct arrow pushing. Yeah, Sarah?
So for the second and third ones, or like for the second one, you know that that's Markovnikov because the OH attached to to the more stable carbocation,
Yep.
the hydrogen attached to the less stable.
Yep.
And the same with the bottom one, the OH attached to the less stable, meaning that the hydrogen attached to the one on like this end of the bond, so that's
Yep. You got it. Yep. Is it about this one? We'll come back in a second. Questions about this? Yeah. No, you're good? Okay. Is it this one? Okay. I think we're looking at 2015, number 14. Is that right? Yep. All right, so this is 2015, number 14. Okay, so 4 alcohols are shown below. Yeah, this one's a little trickier because it doesn't give you starting material. Again, didn't write this exam, so. Let's see. So, so what do you think for the first one? We're not giving a starting material, but you could probably come up with a starting material that could lead you to it, right? So we know it's the addition of water, and so we know we can do the the Markovnikov addition of water to, say, this alkene, right? And that would lead us to that product. And so what letter would allow us to do the Markovnikov addition? A could. What else? B also could. So here's a case where it could be A or B. You wouldn't have to put both. Just one is fine. All right. So for the next one, they're showing explicitly that we have an addition of an alcohol, and then the hydrogen that's been added. They're showing that to show that it's anti. Okay. So have we learned some way that we could add basically the alcohol here anti? So what about oxymercuration? Is that syn or anti? Yeah, that's anti. In fact, it might be nice in these cases just to write down what the possibilities are, right? So stereoselectivity, we'd have anti. What about for BH3, syn or anti? That's syn. What about for acid catalyzed? Yeah, there's none, right? Okay, so it seems like we could do the anti-addition, but like someone, I think Rhea pointed out, it's have we undergone a Markovnikov or an anti-Markovnikov addition? So we've added a hydroxyl group to the secondary carbon while adding the hydrogen to a tertiary carbon. And so that's not Markovnikov, right? That's anti-Markovnikov. So, all right, so if we're going to add anti, but oxymercuration follows Markovnikov, and this follows anti-Markovnikov. Is there any way basically we could add such that we added anti-Markovnikov and anti? Unfortunately not. And so in this case, I believe we would end up with D. Just not possible. All right. Of course, A also adds Markovnikov. Yeah?
I don't know if this was an error on the P, but for the part A, it also had C as an option.
So, let's see. Let's think about that. So we could imagine, I guess, this alkene. And so if we did a hydroboration, oxidation of that, we wouldn't have any regioselectivity. So yeah, I guess C would work in that case. So really any of these methods could lead you, given some starting material that you were expected, I guess, to come up with. All right, so for then the next one, the third one we've got, all right, so this could have been the addition, a syn addition. And so it is Markovnikov. And so furthermore, just back in the instructions, it says that write the letters that would produce the alcohol in high purity, so relatively free of constitutional isomers and diastereomers. So what do you want to do that we could go syn and Markovnikov? Or it could be syn, it could be anti-Markovnikov, right? I guess it doesn't matter because we don't have stereochemistry here. So it could be syn or anti. And so yeah, A would get us there for sure. And then, yeah, B would get us there for sure. It would have been hard to get one of these wrong. There's a lot of right answers in here. Okay, so then finally, we're doing, all right, so this last one, is it Markovnikov or anti-Markovnikov? Yeah, so we're anti-Markovnikov. And so is it syn or anti? It is syn, right, because we've got this hydroxyl group, I'm sorry, that hydrogen and that hydroxyl group. And so what gives us anti-Markovnikov and syn? Yeah, hydroboration, that's our only option there. That's the only one that's leaving the product. Yeah?
How do we know it's going to be free of constitutional isomers?
It's just, I think it's just basically indicating that it's these products relatively exclusively that would be produced.
But wouldn't A produce like other things?
Right, so A, so let's think about that. All right, so for A, if we add to this one, we'd get the same product using the acid catalyzed hydration because we'd only form one stereocenter there, and they don't indicate stereochemistry. Oxymercuration, again, so for this one it doesn't really matter because we're only forming that one stereocenter anyway, so we're only going to end up with two possible products in the end. And I think all three of these could lead to those, all three different, or two different products. This one, I think still could be A and B there. Yeah. Yeah. Yeah, any last questions about this one? All right, new questions. Yes.
So same exam, but 15C.
15C. Yeah, so we've got an alkene, we've got a starting alkene, and we're doing the addition of water. And so is it Markovnikov or anti-Markovnikov? Yes, definitely the anti-Markovnikov addition of water. And so what reaction have we learned can do that? Yeah, so we'd say we've got hydroboration followed by oxidation. And so is that, is a hydroboration oxidation syn or anti? It's syn, we just know that as a rule. It's a concerted mechanism, so. Yeah?
A question about just hydroboration mechanisms in general. Do you need both the H2O2 and the NaOH, or is that either or?
So I think with hydroboration oxidation, you have to use both. But honestly, I think as long as I see one of them, you'll probably get full credit. I'm not a stickler too much on workups.
Can we just start workup?
You cannot use workup because specifically for like ozonolysis, it matters, right? So I do want to see, if it goes through an oxidative workup, I want to see some peroxide. Yeah. Because we've also seen a workup, right, that used sodium borohydride, which is actually a reductive workup. So the workup does matter. Questions about that? Yep.
How do you know it's oxidative?
So you can kind of guess that it's oxidative just because we know we're going to go through an intermediate that looks like this. And so we know we lead to this product. And so generally speaking, if you add an oxygen to a molecule, it's going through an oxidative process. So, yeah. Yep.
Can we go over how to identify if it's Markovnikov or anti from just the product?
Yeah, and so let's see, for example, if we have an alkene that looks like this, and so we look at the product, and we know if we did a Markovnikov addition, let's use, we'll use H2O and catalytic acid. So we know that we're going to end up adding to we've got tertiary versus primary. So in a Markovnikov addition, we know that we've added our alcohol to that tertiary carbocation, right? And so if we went anti-Markovnikov, and we only know one way to do that, which is the hydroboration, so BH3, H2O2, NaOH. In that case, you add it to you're going to end up with your product, the hydroxyl group on the less substituted, and so we end up with that product for the hydroboration. Yeah, so really what you can do is you can think about, in the case of the alcohols, where does the alcohol end up? And so is it on the more substituted? Then it's just regular old Markovnikov. If it's the less substituted, we've got anti-Markovnikov. Yep. Oh.
Is there an example where it came from instead of oxidative?
For hydroboration?
Yeah.
Not in this class.
Okay.
Yeah, we're always gonna, and that's the good thing about the hydroboration is it allows us to access anti-Markovnikov products. That's the utility of it. So we're almost always gonna want to oxidize it. Yeah. Yes.
Can you go over 3 on the same step?
Yeah. Okay, so prioritizing, and so they're all connected initially to carbon, so we won't worry about the first carbon. So the first structure, we consider it connected to 3 oxygens. The second structure is connected to 1 sulfur and 2 hydrogens. The third structure is connected to 2 oxygens, 1 hydrogen. And the final structure is just connected to 1 carbon and 2 hydrogens. Okay, so what should be number 1 for sure? Yeah, and so we look at the first point of difference. The difference is we can just look at the heaviest atoms. Here it's an oxygen, here it's an oxygen, here it's a carbon, but here it's a sulfur. And so we look over at our periodic table. Clearly, any of these that contain a sulfur is going to be first, and so that's what it is. So we'll have, this is 1. Then what's next? It should be the one with 3 oxygens, right? Because if we compare this one and this one, all right, the first connectivity is a couple of oxygens, that's the same. Second one's a couple of oxygens, that's the same. And so end up, we're comparing the final oxygen here with the hydrogen there. And so clearly, the oxygen outweighs the hydrogen. So that's 2. And it should be relatively straightforward to see that would be 3, and that would be 4. Hopefully that's one of the answers. Yeah. Yep.
Can we do number 11 on the 2014 exam, the Fisher projection?
We're not going to do any Fisher projection ones because there just aren't going to be any Fisher projections on the exam whatsoever. So, yeah. Danny?
Can we go back to the that we were on before this one, so 15? So
Okay.
that one, the very first product, in our notes you said that osmosis was non-stereosolic.
Yeah, I had some questions about this, and so I think on the key, this is listed, an ozonolysis reaction is listed as having syn stereochemistry. And so I think that, the writer of this exam looks at it a little different than I do. I look at the final product and did the 2 things add syn or anti. This professor, I think, focuses more on mechanistically, right? And we know the first mechanistic step of ozonolysis is a syn addition because it's concerted. Needless to say, you're not going to have to make that sort of distinction on the exam.
So mechanistically, some of them could be syn, but then the product ends up being weak.
Right, and it's like when we added, when we did a bromination. So for example, in a bromination reaction, we could end up with, let's see, this product, or really I guess a better example would be to do that. And so we'd end up with this product plus this product, and so ultimately that would be plus an enantiomer. But ultimately, I mean, there's no way to look at that product and easily classify it as Markovnikov or anti-Markovnikov, right? Because we added the same thing. There's got to be a way to distinguish, I guess, what we've added. And so, mechanistically, we know that our incoming nucleophile will add to the carbon that would be the more stable carbocation. So mechanistically, it goes through, I guess, a Markovnikov type addition. But I just leave it out, and we just don't even worry about it. Yeah. Yeah, just focus on the products for this class. Shadi.
Can we do number 9 and go over why it's not optically active, or not optically active?
Yeah, so in this case, it's a little tricky, right? Because on the right side, I've shown that we can end up with, let's see. So we can end up with those 2 products, right, on the far right. So clearly those individually are not optically active. But I think that this was just taught a little bit differently in that, so if we do this reaction, we're going to end up with both, because both are a possibility, right? So furthermore, we're going to end up with 50-50 mixtures of both. And so what is a 50-50 mixture of enantiomers? It's a racemic mixture. And is a racemic mixture optically active? No. So that's, you know, again, there's a few nuances that I teach a little differently from this professor. But yeah. All right. Really, is there anyone that feels like they've had their arm up for an hour and I just haven't gotten to them? You can be honest, because I don't see everyone. What about a half hour? 20 minutes? Don't be. All right, it's a free for all. I see you. Yeah.
Could we go over from 321, question 1?
321, question 1.
We've been over it before, but I don't understand why the answer is what it is.
And so, let's see. Which one? The top one or the bottom one?
The bottom one.
All right, so in the bottom one, what we've got is, so let's see. All right, so we can draw out the mechanism for this. I'll do it up top here. So we've got our starting material. Well, maybe I should draw it at the bottom so we can keep some order here. So this would be number 3. All right, so we're adding HOCl to that double bond. So mechanistically, let's see how this thing goes. So we've got hydrogen. That's one. All right, we'll draw the same way. Is that the starting material?
Yeah.
Okay. All right. So first off, what type? I mean, we gave this type of reaction a name. What is it? It's a halohydrin reaction, right? So we know we have HOCl. So what's the first step of this? Where's the first arrow always?
From the pi bond.
From the pi bond. And so is it going to go to the chlorine or the hydroxyl? Chlorine. The hydroxyl's kicked off, and so then the chlorine does what? It adds back in, right, so that we can form a chloronium ion. So that'll add back in. And so from the perspective of this first step, is this going to be a syn or an anti-process?
Anti.
So this first step, we're doing everything at once, right? And so what that means is that we're going to end up with our chlorine on the same side. So if we keep our carbon structure there, we can say, show it on a wedge there and a wedge here, and so ultimately that methyl gets pushed back to being on a dash. Okay, so the first step here is syn, but the ultimate stereochemistry is not syn, and so we'll see why that is now. So now what we've got is our hydroxide. Got to remember to have our positive charge on our chlorine. Very, very important. All right, so then we've got two possibilities, right? We can add our hydroxyl group to the tertiary carbon or the secondary carbon. So which do we add to? This has been giving people some trouble. All right, so we've got a secondary here and a tertiary here. So let's think about what a secondary and a tertiary carbon, what their stabilities would be, right? So we have our structure. This is how we remember which it adds into. So what we're going to have is an equilibrium. And so our equilibrium is two other structures. So we've got this possibility. Which forms a tertiary carbocation. And then we have the other possibility that it can be in equilibrium with. And so that is a, what type of carbocation?
Secondary.
Yeah, that's a secondary carbocation. I should put that in blue. All right, and so which of those structures do you think is going to be more stable and exist more? Yeah, definitely the one on the right. So this is the more stable structure. And so because that's more stable, we end up with an electronic nature up here of our tertiary being partial plus and our secondary being partial negative. And so knowing that, now which are we going to add our hydroxyl group into? Definitely the tertiary. And furthermore, is it going to add from the front face or the back face? It has to add from the back face because we're displacing a bond, right? So we've got to have the backside attack. And so what we would end up with would be our hydroxyl group on a dash, our methyl pushed forward, and then our chlorine forward. And so ultimately, we describe the stereochemistry of this product as syn or anti. Definitely anti, right? So all type 3 mechanisms end up as anti-products, even though this first step is kind of like a syn, but right, we don't end up with that syn stereochemistry. We definitely end up with the anti-stereochemistry. Lots of hands up about that. Yeah?
Would you explain where you're adding the bottom again? The hydroxyl?
Why we're adding it to the tertiary?
No, like from the bottom.
From the bottom. And so what it is basically, you know, if you're gonna displace something, if we're gonna push this bond right here away, it's going to be pushed from the other side. And so when our incoming nucleophile comes in to kind of push the other bond away, it has to come in from 180 degrees of it. So what we've got here is a chloride that's sticking down and on a wedge, right? So it's kind of like that.
So the chloride is on like a wedge, or in a dash if you go from the top?
Yep, it's just always the opposite. So if you've got your chlorine that's on a wedge, we've got to approach from the back side, which puts our hydroxyl on a dash. If you've got your chloride on a dash, our water has to come in from the front side and displace, and so it ends up on a wedge. Yeah, so that's why we end up with our halogen and our water, or at least our hydroxyl group, anti to each other. That's why we get anti-stereochemistry in a halonium type mechanism. Oh.
The most stable of the three on the bottom is the one in the middle, right?
Well, yeah. So this is, the middle one is definitely most stable.
Would you ever give us something where we have to decide between three things like this, where it's partway through a reaction?
I think that'd be totally a fair question to ask. We should know that the middle one's most stable because it's closed shell, and then this one here is the second most because it's tertiary versus secondary. That'd be fair.
Okay.
Yeah. But more likely what I'm going to ask you to do is know that by showing me the product of the reaction. Basically, this determines regiochemistry. Yeah. Maria?
So in all bridge halonium reactions, we're going to show displacing of the bond with that arrow, right? Like when it picks one side to go to, we do show that.
Yeah.
Okay.
Yep. Other questions about this? Okay. Yeah, and so the most likely case that you're going to see any shifts on the exam, you might see something like this. You might be given, oh, we've got starting material that looks like that. We hit it with some acid. And so what we end up with is this product, right? And so if we look at these carbons, we see we've got primary, secondary. This is a quaternary carbon. And so it doesn't really initially make a lot of sense that we could end up with this connectivity, right? Because we've got a carbon here that's ultimately connected to 4 carbons, and here it ends up connected to 3. And so likewise, this was a secondary carbon. It's now been turned into a tertiary. And so what we know must happen is some sort of shift because we're changing our carbon connectivity. And so, you know, if you're ever stuck in this sort of situation, just go ahead. You know what the first step will be with strong acid, right? We protonate the double bond. So we just go ahead, protonate our double bond. Let's make that an X. If we protonate our double bond, we know we'd end up with a Markovnikov addition such that we formed our secondary carbocation. And so is there any shift we could do to basically get to this connectivity? Yeah, and so in this case, what we could do is undergo this 1,2 alkyl shift. And it's 1,2 because of that numbering right there, right? So we had a methyl group on a 1, and so it's going to walk over to a 2, so that's a 1,2 methyl shift. And so is there a driving force to do that? Yeah, so thermodynamically what we've done is we've gone from a secondary carbocation to a tertiary carbocation. So absolutely that's going to be a favorable process, and so eventually we would just snap our X to that tertiary and we end up with a product. So this is, I mean, this is most likely what could happen is I'll show you a starting material or product and ask you, how's that? Yep.
What is the radioselectivity of a halide flat?
So that's Markovnikov. Pretty much we call everything Markovnikov except for hydroboration. Yeah. And it has to do with where the nucleophile electrophile combo ends up. Yeah.
Would you be willing to do the arrow pushing mechanism for the concerted reduction mechanism, where it just ends up with the two H's?
So you're not responsible mechanistically for the reduction, and really it's just beyond the scope of this class because that platinum metal stuff does weird things that don't follow our rules.
On the exam, number 2, 2015, question number 1 is also the least exothermic reaction. Can you explain that?
So that's just material that we didn't cover. So this stuff you wouldn't see that type of question. Yep. Sarah?
Can we do an arrow pushing mechanism for halogenation?
For halogenation?
Yeah. And specifically, we say in our, like when we do the arrow pushing, can we also go over, if we have in our chart that its regioselectivity is sort of Markovnikov?
Sure.
I forget what
It's one of those things where we end up with, we add a halogen here and a halogen here, and so looking at the product, there's no way to tell which added where, right? But we know that mechanistically...
You add the first one Markovnikov.
What's that?
What, does it mean that you add the first halogen to Markovnikov?
Well, it means that the nucleophile is going to add to what would be the more stable carbocation, right? And so that's for the same exact reason that we just looked at when we did our halohydrin reaction, right? Because we know that our nucleophile is our OH group, and it adds into the more stable carbocation, even though that's a minor structure in the scheme of things. What are we doing? We're doing a halogenation. Okay, so for halogen, do we want to do cyclic or acyclic?
Whichever is harder.
I mean, I've been hearing that acyclic is harder, so we can look at an acyclic. So let's just start with a simple E double bond. And so we'll do the acyclic. And so again, I think it's easiest to see these acyclic mechanisms if you go ahead and rotate it such that we have wedges and dashes. So this would be methyl. This would be methyl, hydrogen in front, and hydrogen in back. So here, you know, what halogen do we want to use? What halogens can we use in a bromination?
Chlorine or bromine.
Chlorine or bromine, what do we want to do?
Chlorine.
Chlorine, okay, so if we add chlorine, we'll go ahead and add from the top face. So our first step, we're going to start an arrow where?
Double bond.
From the double bond. So where's that double bond arrow going to go to?
One chlorine.
One of the chlorines. So we'll kick off the other chlorine. What's the third arrow that's necessary in a halogenation?
The chlorine flow.
Yeah, it's from the electrophilic chlorine back to one of the carbons. And so that guy looks just like that. All right, so what happens to all the substituents here? They get pushed down, right? Because our chlorine is added from the top face. Of course, at the same time, half of our molecule is going to be added to from the bottom face, and so we'll say plus nanotube. But we only have to show one. And here's another thing. Mechanistically, on your mechanism tomorrow, you only have to show the mechanism going to the one product that I'm asking you for. You don't have to worry about other stereoisomers that would be possible. I'm going to show you a specific starting material, a specific product. Just get to that one. Don't worry about other things that could form. When you're doing mechanisms, we don't care about what could form. We care about the reaction that's right in front of us. All right, so let's see. I'll go ahead and draw in our carbons here. So we've got chlorine on the top with a positive charge. Everything's been pushed down, so methyl, hydrogen, methyl hydrogen. Okay, so here we have another chlorine waiting to come in.
Why does the hydrogen change from a dash to a wedge?
Because I messed up. Alright, there we go. Alright, so then we want to displace that chloride, and so in this case they're both secondaries, and so this is one that could potentially give you a lot of stereoisomers. So we're not going to worry too much about the possibilities, because again, I'm not going to ask you to draw like 8 stereoisomers on the exam. We don't have time for that. So don't overcomplicate it, but what we can do is add to one of the carbons here. And so in doing so, if we're going to add into the right carbon, what's going to happen to those substituents? Yeah, they're going to get pushed out, and so we end up with a hydrogen up, methyl up, a chlorine in the plane, chlorine, methyl, and hydrogen there.
And does the chlorine have to add to the bottom if the other one's at the top?
Let's see what happens. Well, yeah, so if we have this intermediate, then we must come from the bottom, because it's got to be anti, right? It's got to approach and displace it from an anti alignment. So, yeah. And then, of course, let's see what happens if we add to the other carbon, just for fun. This is what we do for fun. Right? Sure. All right, so in this case, we would end up with substituents pushed up on this side. So methyl, hydrogen, chlorine, carbon, chlorine, hydrogen, and methyl. So how are these things related? That's a good question. How are these things related? So what if we took this thing and we did this? Ready? Just flip it over like that.
Oh, they're the same.
Yeah, those, and so it doesn't matter which carbon we add to in this case, those are just identical.
Is there ever a situation in this when it would matter which carbon you added instead of chlorine to?
Yeah, so in this case what we've got is a really symmetrical alkene, right? Because we just have a methyl group there and a methyl group. But say then we put an ethyl group there, then we won't have that symmetry where we could just flip it over.
Right, so how would we then know which carbon to add our second?
That's a case where I think you'd get a lot of stereoisomers, and I wouldn't expect you to. We're not, I'm trying to keep it relatively straightforward. So, Chris?
So for this one, if you gave us that starting material, we would just write one product. We wouldn't have to write plus enantiomer or plus diastereomers or anything like that.
So it's still going to be plus enantiomer. Why? Because here we could have added from the bottom face, right? And so we would have the chloronium on the bottom, and so that would be the enantiomer there. So you're going to get one product ultimately from this chloronium, and you'll get one product from its enantiomer, and so those two products should be enantiomers of each other. Yeah. Yeah?
In this propyl-hydrogen reaction, why generally is H2O more nucleophilic than the other ion?
Because it's more basic. And so think about it this way. We've talked about the inverse strength of acids and bases, right? So HCl, really strongly acidic, H3O plus, strongly acidic but not as strongly acidic, right? And so if we draw that out, we're comparing ultimately their conjugate bases. So, their conjugate acids. So what we've got is we're talking about why is H2O more nucleophilic than Cl minus, right? Is that kind of, yeah, and so what it is we don't know much about the basicity, but we know a ton about the acidity, and so we know we have our pKa table, which will be supplied. I don't think it's too necessary, but it'll be supplied. The conjugate acid is H3O plus. Here, the conjugate acid is HCl, and so pKa of these things, this is right around minus 1.7. This pKa is minus 7. Something like that. And so what's the stronger acid? It's definitely HCl, right? So we've got our stronger acid here. What's the stronger base then? Yeah, so our stronger base is going to be this one up here. And so, like Hope had brought up earlier, we find that nucleophilicity and basicity are very similar to each other. And so because this is so much more basic than this, then this is also a lot more nucleophilic than that. Yeah, I've harped a little about acid-base importance in organic, and it is. It's a lot of stuff comes from acid-base reactivity. Yep.
Can we go over like the basics of what's optically active?
If you're ever asked yourself, or if you're ever just laying in bed and you ask yourself, what's optically active? You ask yourself, does it have an enantiomer? All right, and so if something has an enantiomer, it's optically active. If something does not have an enantiomer, it is not optically active. So anything chiral with an enantiomer must be optically active, and then the opposite is true. If it's achiral, it is not optically active. The only real tricky case, so let's see, we've got meso compounds that have chiral centers, but are they chiral molecules? They're not. And so does a meso compound have an enantiomer? No. No. So would we expect it to be optically active?
No.
No. We've also learned that a racemic mixture, right? That's a 50-50 mix of enantiomers, and so the specific enantiomer is optically active, right? But when we have a racemic mix, they ultimately just cancel each other out. And so in a racemic mixture, we see no optical activity. And that's pretty much it, I think. Yeah?
Can we go over cycloalkene?
What was that?
Cycloalkene
Nomenclature?
with substituents?
Yeah. Let's see. What date was that homework?
March.
Okay. Yeah, I haven't been asked to do any of these. Got one in mind?
Can we do with the iodine and chlorine?
So we're looking at this one right here?
Yeah.
Yeah. Okay, so it's the cycloalkene. So first and foremost, when it comes to cycloalkenes, where do 1 and 2 have to go? 1 and 2 have to go to the double bond. So we've really got two possibilities in this case. I'll redraw it a little bigger. All right, so we've got a structure that looks like this. And so we know that we've either got a number 1, 2, 3, may as well go all the way, 4, 5, 6, or we can number 1, 2, 3, 4, 5, 6. Now generally when we're talking about numbering, how do we know if we go clockwise or counterclockwise? We look for the first substituent that we would hit, right? But here we've got a case where, all right, if we use the blue numbering, our first substituent will be at this iodide on 3. And so up here, it's also going to be our first substituent at 3. And so while maybe not explicitly stated in class, how do you think that we would tell the difference between the iodine and the chloride? It's just alphabetical, right? We basically, when everything else is even, we can just roll with alphabetical. That's kind of our last resort. And so, how would we number? Blue or red? Blue or green? Green, right. And so that gives our chlorine, which comes first alphabetically, the lower numbers. So let's go ahead and name it. So this would be 3-chloro, 6-iodo. And so do we have to say 1 cyclohexene? No, because we already know that we have to give the double bond 1 and 2, so we don't. That's unnecessary. So we could just say iodo cyclohexene. Have we named that specific molecule?
No.
Unfortunately not. They're stereocenters, and so here we prioritize 1, 2, 3, 4. Is that R or S? I see S. Right? So if we put our thumb back with our hydrogen, we can curl with our left hand, 1, 2, 3. Also, we can see that it's 1, 2, 3 counterclockwise with 4 in the back, so that would definitely be S. And then up here we've got 1, 2, a lot of numbers on here. 1, 2, 3, 4. And so would that be R or S? Yeah, that would be R. And so how we would name this is to the front we add all of our stereochemical information. And so in parentheses, we would say, I don't know, what would we say?
3R, 6S.
Yeah, we'd say 3R, 6S, and then just name it like usual.
Would we care about like Z though?
So in this case, would we ever have the E double bond? No. And so because we know that only the Z double bond can exist because it's in a 6-membered ring, it would be redundant information to call it. Now, could we assign an EZ label to it? Yeah, absolutely. It's definitely a Z double bond, but we just don't have to call it a Z double bond because everyone's going to know that it must be a Z double bond if you were talking about it. So, yeah. So you're talking about, are you talking about the stereochemistry here and here or the double bond? So you're talking about the substituents we have, and so we only are going to use cis trans for a ring like this in cases where it would be this structure and this structure. And the reason is these two positions are now not chiral centers. And so if we can't give chiral centers to them, the only thing we can do is say, well, you know, we can't give this RS, but we can say that it's on the same side as the chlorine. Right, yeah. And so if by removing the double bond, we have a ton of symmetry that we've given now, and so that's eliminated the chiral centers, and so we can say cis or trans there. Yeah.
Can you do the last one on that same row? The chlorine?
So this one?
Yeah.
This is a good one. So, do we always have to include the double bond in the longest chain?
Yes.
Yeah, and so what that means is that we're not going to be able to count from end to end because by doing so, we're not using this double bond in the chain. So, our options are to say 1, 2, 3, 4, 5, 6, or, not use red, 1, 2, 3, 4, 5, 6. And so would we use blue or red?
Blue.
Yeah, so we always want a number such that we can give that one of the alkenes the lowest number. And so we definitely want to use our blue numbering here. And so what that means is that if we use the blue numbering, what we've got is a 2-butyl, a 3-chloro. And so the stereochemistry of that chlorine is what?
Yeah.
2, 3.
R.
Is it R?
I think.
Oh
wait, no.
I see S, right? So if we put our thumb towards us for 4, we can count 1, 2, 3 with our left hands.
Whatever's the H1CO. Yeah, S.
Disagreements? We're good S?
Yes.
I mean, we can make it even bigger. Let's just, what we've really got is we've got something that looks like this, right? We've got 2, 3.
Why is that one 2?
So that one is, good question. Let's talk about that. I think it's going to be 2 for reasons that...
Is it because of the end of that double bond is a carbon as opposed to 2 hydrogen?
Yeah, this is way more advanced than I give you on an exam. But I think ultimately, so what we've got is this carbon is connected to 2 carbons, and this carbon is, well, wait a minute. Yeah, so that, I think, yeah, goes backwards. 2.
Wait, why? Like, why?
Yeah, so now what we've got basically is our structure looks like this. And so here we've got a carbon that is connected to 2 C's, 1 H. Here we've got a carbon that's connected to 3 C's.
Okay.
Yeah. Yep. So in that case, this is really 2, 3, and so that would be R?
Yes.
Okay. All right. We're happy with that. This is R. So in naming it, so our longest chain is how long? It's 6, and so what's our prefix? Hex, and so it's going to be hexadiene. So we would say, let's see. All right, so we put our stereochemical information first. So we also, I mean, we didn't talk about the stereochemistry here yet. Do we have stereochemistry?
Yeah.
Sure. So we've got, is that E or Z?
E.
That is E. All right, so we decided we're using the blue numbering. So what we're going to end up with is 3R, 4E.
Does it matter which one goes first?
I think technically the lower number is supposed to go first, but you know, as long as the stereochemistry info is there, that's the important part. So 3R, 4E, and then 2-butyl, 3-chloro. And so where are our double bonds here? What numbers?
1 and 4.
1 and 4. So we'd say 1, 4, hexadiene.
What if we just said 4?
If you just said 4 hexadiene, you're not. So technically,
Like the dying tells you that there's 2.
there's got to be 2, right? And so I was trying to think of how, in reality, it couldn't be here because then we wouldn't have that chiral center, which means it couldn't be here. And then I think they named back-to-back double bonds separate. So it might be slightly redundant, but here we should definitely name both. Yeah, I think technically it could be just a touch redundant. But again, that's outside the scope. Yeah.
Is there no EZ in the second double bond?
You talking about this double bond? Yeah, so because the top side is 2 H's, there's no way to do it. Yeah, there's no stereo. Yeah.
Is it hexene only if there's only like 1 double bond, or is it always hexadiene?
So when it's 2, it turns into hexadiene.
And then if it's more, then...
If it's more, we could have hexatriene or hexatetraene.
Okay.
Yeah. Yeah.
Will you run the arrow pushing of a hydroboration mechanism?
Yeah. We're still recording. Yeah. So these 2-hour workshop videos are like half a gig. So they're huge. All right. Hydroboration. Let's see. Let's do an acyclic. Let's just do a simple. Actually, let's use the Z double bond. So let's say we're gonna hydroborate this structure. Well, we need to give some sort of. All right. So let's say we'll make that a methyl. Okay, so that'll be our starting material. So what we've got is a tertiary versus a secondary carbon there. And so the boron or the hydrogen, what do we learn is more electronegative? Hydrogen, right? And so in terms of charges, we've got a partial positive, partial negative. And so the way that these will line up is our hydrogen being more electronegative will be attracted to that side, and our boron being more electropositive will be on the right side. And the reason is we have negative there, partial positive there, and so we can see that these two things like each other, and so do these two things, and so those are going to be on the same side as is. All right, so mechanistically, how are we going to draw this? Where do we start an arrow? Or the pi line. And specifically, are we going to draw to the boron or the hydride?
Hydrogen.
So what's an electron going to be more attracted to? Slightly positive or slightly negative?
Slightly positive.
Yeah, so we'll draw it there, and then our hydride. And I say hydride, why? We're including the 2 electrons, right? That's what's actually moving is the proton plus 2 electrons. So we define that as a hydride. So we have a hydride moving there. So what we end up with, the substituents, they're all going to be pushed where?
Down.
Yeah, they're all pushed down because as a concerted mechanism, these things happen at the same time. And so it has to be the same phase. So we have methyl, hydrogen. BH2, methyl, hydrogen there. Okay, plus what? Yeah, because we could add from the bottom face, and so how many chiral centers are we creating in this intermediate? It's just 1, right? Because over here we're actually connected to 2 methyls, so it's just going to be this chiral center would be flipped, so we'd have plus an enantiomer. And so then, this is a stable intermediate, and so what do we add to our reaction? Well, that's our hydrogen peroxide, sodium hydroxide.
Yeah.
Should be our work up there. And so what do we do? What does that do?
Replaces the BH with that, right?
Yeah, and so very, very, very importantly, does the stereochemistry change at that carbon on the right?
No.
It does not, and so we retain that stereochemistry. And we haven't learned a way that we could swap out two groups and retain stereochemistry, right? So we don't even talk about mechanistically how it happens because we haven't learned it. But importantly, we say that it does. We do retain stereochemistry. And so we end up with the ultimate product where we've done syn addition. And so typically we consider our hydroxyl group as a nucleophile, right? We've never seen a hydroxyl group as a water-acting electrophile. And so ultimately we end up with our hydroxyl group on our secondary carbon here. And so we consider this Markovnikov or anti-Markovnikov. It's anti-Markovnikov, right? And so again, it's strictly from the point of our products, I guess, that we're calling that anti-Markovnikov. Yeah. Is it about this?
Yeah.
Yep.
So can you actually draw the methyl and the hydrogen later and then draw the
Yeah. Yeah. And so we don't have to show the wedges and the dashes on the left side. In fact, what we could just show. I guess we'd have to do. Okay. It might be easier just to do a line drawing. Right. So that's the same thing. We don't need to draw wedges and dashes here because we don't have a stereo center. And then we're showing our hydroxyl straight up in the plane, the same orientation here, and so we show our methyl. We're showing all the stereochemical information present in both drawings here. Yeah?
Can we do number 7 on the 2015?
2015? All right, so do we know a way to make diols? Yeah, that's osmium tetroxide, right? And so, you know, we only know one way to make diol, so it must be osmium tetroxide. And then what best describes the product's forms? What do you think? Well, first off, do you think that one of them will form, or do you think both will form? Both will form, right? We could add to the top side of the alkene or the bottom side of the alkene. And so since they'll both form, we need to figure out what the relationship between them is, and what is that relationship? Why aren't they enantiomers? Yeah, we already have this chiral center that's not changing at all, and so that since there can't be mirror images, we have diastereomers. Yeah?
I have a quick to 9. You said if you have both products that are in enantiomers, it's still optically active. But the answer to this was supposed to be no, at least.
Yeah, and so this professor taught it slightly different, and so she was emphasizing the fact that we would end up with a pair of enantiomers that technically is a racemic mixture, right? And so a racemic mixture is not optically active. But typically what I focus in on my questions is I ask you about one of the products, and I ask you, is that product optically active?
Okay, so it's just crazy.
It's just different ways of asking a question. Yeah.
On number 15, the second one, it said there was a racemic mixture, but I thought it was chiral, so I don't understand how that can be.
This one right here?
Or not chiral, yeah.
So let's see. It's the acid addition, so we would end up with this product. And we would end up with this product. So what's the relationship? Is there a chiral center?
Yeah.
No, so there's not actually a chiral center in this because of the high degree of symmetry, right? So those are actually the same molecules. And so if we don't have a chiral center, can we have a chiral molecule? No. And so if we don't have a chiral molecule, would it be optically active?
No.
So these are the same product. Yep.
It said that it was a mixture of an anti-mix though.
Nah, it's not.
Okay,
I don't know. It's not mine. Yeah, it's definitely not, because, you know, neither of these can have an anti-mix. Because they're the same thing. So, yeah. Beats me. Yep.
So, for an ozolytic reaction,
Start over.
for an ozolytic reaction, how do you know on which side of the resulting alpha-alpha carbonyls will be?
So you're asking about ozonolysis?
Yeah.
And so we formed two products, and so how do we know what?
Like, you know how there's the two double bonded oxygens?
Yeah.
How do you know like which will be on? Will they both on the same side of the resulting alcohol? Will they be how do you say like anti-acidic?
Yeah, and so it doesn't matter because we won't end up with stereochemistry there. There's no way to assign stereochemistry to a carbonyl group with the CO bond. So no matter how you draw that, you're drawing the same thing.
Okay.
Do you have a specific example of that?
Just for one of the homework issues, we broke a cycloalkane into a normal alkane, and one of the carbonyls is on one side of the alkane, and the other one is anti.
Yeah, and so I think I understand what you're getting at. So you're saying, that, for example, we break this thing open using ozonolysis, so we have O3, and then we'll do a reductive workup, so that's dimethyl sulfide. So it's all about cleavage, so we cleave our alkene. And so in these cyclic examples, alkenes, in these cycloalkenes, you're going to end up with one product. And the reasoning is that when we cleave this right side of the double bond, or that cycloalkene, we're still not touching the others, right? So we're still connected together through the rest of the ring, more or less. So what we'd end up with is 1, 2, we'll just name 1, 2, 3, 4, 5, 6. So in our resulting product, we're going to have a carbon chain that's 6 carbons long. 1, 2, 3, 4, 5, 6. And so we're going to have carbonyls on carbon 1 and carbon 6, so we could draw that, right? That would be our product. However, you could draw, there's no stereochemistry in this molecule, so you can orient these things however you want. You're going to have this, it's the same product every time, and it's just because there is no stereochemistry. And so if the connectivity is the same, it must be the same molecule. Does that answer your question?
So if there was enough of possibly one carbon, would there still be no stereochemistry?
Yep. And so that would be there, and that would be there, right? But we can't assign, say, EZ stereochemistry because here it's just 1, 1, 3, right? So. Yep. Yeah.
Could you do an example with a reduction with H2 in a metal when there's 2 double bonds?
Yeah. And so basically, if there's 2 double bonds, so let's say we have like cyclohexadiene, we react that with H2 and palladium, more or less, you're just going to end up with your cycloalkane. Just like that. So you're going to reduce, and so specifically, and I know there was a sampling problem. The sampling problem said that there would be excess H2, and so what that meant was that there was more than enough H2 there to reduce both double bonds. The thing that could make this a little more complicated is cases where you have substituents on the double bonds, knowing that it has to be a syn addition. You could end up getting different stereoisomers there. But I think the important thing to keep in mind, because I'm probably not going to ask you, you could end up with a lot of products, and I'm trying to stay away from that sort of thing on the test. So typically, you'll just, the key point is that you'll reduce both bonds.
So if you have 2 bonds in the test, and you have H2,
Yeah, you'd reduce both.
Okay.
Yeah. Sean?
Can we do number 10 on 2014?
Yeah. All right, we're looking at number 10 on 2014. And so we've done it a little bit already. So essentially, All right, so this is the reaction of an alkene and acid. And so we've got a couple of different types of intermediates, right? So we've got carbocations for A and C, and then we've got a chloronium for type B. So knowing that it's the addition of an acid, we know it's a type 1 mechanism automatically, right? We have to be going to the carbocation. So that eliminates B. And so then what we've got is we've got a carbocation on this secondary carbon, and then a carbocation on this secondary carbon. And so you can see that there's a CF3 group here, whereas next to this one it's just a CH3. So it's the inductive effect in play again, and so remembering that, that a fluorine basically stabilizes negative charge by withdrawing some of it and spreading the charge out, it does the opposite to a positive charge because it's still going to withdraw electron density, but if we withdraw electron density from a carbocation, it's losing electron and becoming more positive, right? So now we're focusing even more charge in one place, and so that's a destabilizing factor for carbocations. So because the fluorine is going to destabilize this carbocation by withdrawing even more electron density, we end up saying that this is the more stable carbocation. So we say A, and then so if this is our carbocation, we're going to add our Cl to the left side, and so we end up with that product right there. That's B.
But then for the third part,
How
would you explain that?
And so this is, again, a little bit different wording. If I were to say this, I would say briefly explain in words why only one pair of enantiomers is formed. And so again, this professor, I think, just kind of considered a pair of enantiomers as being one product, whereas, you know, we've been learning that enantiomers are not the same thing because we can't orient them in space the same, and so I would consider it two products, so I might change the wording a little bit. Yeah. Sir?
Please go over 2015, number 4.
Okay, so, knowing what we know about this type, so it's a halohydrin reaction, and so mechanistically, let's think about what we'll go through. I'm not going to draw the mechanism because we've done that already today, but we're going to go through a polonium intermediate. So then we're going to go through this intermediate before finally arriving to our product that will be stable and neutral. And that looks like that. And so, you know, really what you can do is you can just count the intermediates. So how many intermediates do we have?
3. Oh, yes.
Yeah, so it's 2, right? We actually, the things that we draw in the middle of our mechanism are the intermediates. And so we've got 2 intermediates. A, B, and C, which one has 2 intermediates? C, right? Because intermediates are our values, so we'd have A there and B there. And so it can't be A, or I'm sorry, this A, because there's only 1 intermediate here, and it can't be this one because it's showing 3 intermediates. So I'm just thinking about the intermediates that we'll go through on our product. Yeah.
It's for the reactions you're saying, like, not the final product, it's plus enantiomer, but like the first thing you form could be plus enantiomer, but then it could be top or bottom. But I'm a little confused as to why those are the two.
So you're talking about like right here?
Yeah.
Yeah, so I mean, let's draw the enantiomer out. So when we draw it out, I'm going to say that we've got 2 chiral centers, and so let's check that. So, and I think they're opposite of each other. So between these 2 structures, say this chiral center, have we kept 2 of the things in place? The ring, right? We didn't touch the ring, it's still in place. Have we swapped the other 2 in space? Yeah, and so because we've held 2 in space and swapped 2, that tells us that the chiral center here is going to be the opposite of the chiral center here. And so the bottom one's the same, and so we have a pair of enantiomer intermediates. Enantiomeric intermediates. 12? I don't know. I have no idea what this looks like. So 4-methyl-2-hexene would look like this. So I would say that there are 4 possible stereoisomers. I guess we could have EZ here, and we could have RS there. So that's 2 to the 2, which is 4. So we're asking just about the naming one specifically? So give the IUPAC name, so we would name 1, 2, 3, 4. Oh wait, the one we drew in the blank. We haven't drawn one. In the box it writes, all stereoisomer has the following characteristics. It is achiral. Yeah, we didn't really do anything like this. It contains a double bond that does not show easy stereoisomerism, and it has a methyl substituent. I hate these. What's that?
Is there more than one possible?
Yeah, I got a different
So, I don't know. Just to not, what's the answer? Someone come draw the answers, because I don't have time to.
I have a
spend
different
on it.
answer. I got 2-methylhexene.
You got what?
I got 2-methylhexene.
2-methylhexene?
But that's not what she gave. I got 4-methylhexene.
Alright, so this would be methyl, where's the double bond?
On the first part, like it's a terminal double bond.
So that?
No, the other one.
That one works too.
But there, that's what I drew.
Alright, so you're saying we can do that one, or we can do this one? And you're saying you did 4-methylhexene?
I don't know if that was
Yeah, I don't want to spend a ton of time on this. Which one specifically were you wanting to name?
There was just one answer, but I thought it was
It's possible there are 2 answers. Yeah, we didn't. I don't love these types of problems. So we didn't really do much with them. Yeah, Alec.
Basically draw a ring, or would that have easy just remain the same?
Can we draw a ring?
Just do a cyclohexene.
Well, we have to have a double bond, and so I think that's going to change that'll change the formula. If we have a double bond. Yeah, so that wouldn't work. Yeah.
Whenever one was represented as 4 stereoisomers, they were like SD, RE, RT.
Is it number 4 here? That's all I got. Maybe over here.
Yeah. So I was wondering if that's
Yeah, so an important distinction if you're thinking about enantiomers is that enantiomers are going to have little chiral centers with the same double bond. So yeah, if you look at the pair of enantiomers here, we have RE, and so this enantiomer, we flip the chiral center from R to S, but the E stays the same. And that's just a product of, if you take a mirror image of an EO1, you get an EO1, it's the same.
So why is switching to
Because this and this are clearly not mirror. So we've got here E, here we've got C, and so since those aren't clearly not mirror images, they must be distinct.
So then is that more like a true diagonal?
Say it again?
You drew like a diagonal line between like SD, RZ, and RE and C.
Yeah, so since we've already, out of our 4 total stereoisomers, since we've already located 2 pairs of enantiomers, all other relationships must be diastereomers. Yeah, and that's just because once you have one, you can only have one enantiomer, right? So you can only have one relationship with an enantiomer. So yeah, once you've paired everything off as enantiomers, you're done with enantiomers. Yep. All right, last questions.
Okay, one more. Can you do on
Number 3. No, we didn't cover it. So, Yeah, an example of that is when we have like the halohydrogen reaction where we can add either water or the halogen as a nucleophile. And so we never add the halogen. It's just this along for the ride. It's just there because we formed a polonium which is positively charged, and we can't create charge. We have to separate charge, and so it's just going to be there as a counter ion to that positively charged polonium.
So once an ion stops being relevant, can we stop drawing it?
Yeah, I don't care too much about that. So, I'll say this: you do want to show it. So if you show a bond breaking, so if you basically show something becoming a spectator, you will want to show it because it was involved in the mechanistic
But then,
step.
like, in the next step?
In the next step, I don't really care too much. Yeah.
Okay, so I think we do care about, like, for example, the radioselectivity of the product instead of the mechanism so much. But so, like, for example, if like the mechanism is usually Markovnikov, but it wouldn't matter for the product because like there's no substituent or something, would we be expected to say neither in that case?
I honestly, so in a lot of these exams, you give a product and it's like circle, Markov, right?
Yeah.
Circle, regio, and stereo information. I don't really get into this problem.
Okay.
So,
Okay.
yeah.
Thank you.
Yeah. I'm more interested in not like, I will know that you know what's going on based off your product. I don't need to then ask you, was it Markovnikov? Because you've already shown me the important thing, which product are you going to get?
Okay.
Yeah. Uh-huh. Uh-huh.
So you already did this in March 18, but that's not really how we show this.
So what we can do in this case is keep your halogen oriented the same, so we're just using that for halogen. What you know is because the halogenation is an anti-reaction, that we're going to just show one on the way and the other on the dash.
But if this was a C, would it be like, would you would still be one away on a dash, right?
Yeah, it would still link. So you would end up with different products because now what you've done is you've drawn one side. Yeah, and so now it's good. Yeah, if you don't believe me, just go ahead and see what would happen if you draw out the product. You should end up with different.
It's kind of like question 3 that you asked, but like it's kind of like the first unit. It's not necessarily recovery, but which one would be more stable? You know?
Yeah, so basically alkenes are more thermodynamically stable with more substitution. And so when we look there, we see we've got 2 methyl groups off of this one and there's 2 off of this one. So that doesn't impact things. This should be more stable, if anything, just because the methyl groups are further away in space and absolutely no interaction can occur between them. Whereas these might have a little bit of steric. Great, because even though these look like they're pretty far apart, they both have hydrogens off of them which are rotating, and they might bang together every now and then. Yeah. Yeah, Sarah.
There are just times like we're drawing reactions and
Yep.
you draw the reagents on top of the arrow, like you'll have like your reactant and you'll have your arrow and your reagents like written on it and then
Yeah.
the product. If we're more comfortable drawing it out in front of the arrow so we can arrow push like that, is that okay?
Yeah, it doesn't matter.
Okay.
Yeah. Lena, I would rather answer your questions in person than via email. So why don't you just go ahead? It's going to be a lot faster
I was
for me.
also about to apologize for sending you that because I realized I was like, we just sent a lot of questions. But then I had questions.
Yeah.
Sorry. I also have another stupid question that is answerable for me.
Okay.
But so, could you maybe give an example of a reaction that would be H2O catalytic acid reaction that is messier than the oxidation mercuration reaction? Because the one that we have in our notes has the same amount of products. And my brain just
Yeah, what you could do is something.
very much.
Yep, Caesar. You could do something where basically your starting material maybe looks where you have 4 different substituents off of your double bond. And so now, what's going to happen is with your acid catalyzed reaction, you're going to form both stereocenters on one side and then both stereocenters on the other side, end up with 4 different possibilities. Whereas if we do the oxymercuration, we know we're going to have to add both SEN.
Okay.
And so there would be less products in that case.
Okay.
Yeah.
So if this was also methyl, like, how do you know to which one to draw it? Like the wedge. You wouldn't draw the wedge in the dash in that case?
If which was a methyl?
If this was a methyl. If this wasn't a methyl.
If that was a methyl, then you wouldn't have a stereo
Yeah,
center,
okay.
and so you wouldn't have to worry about it. Yeah. All right, you guys can ask questions while I start packing out.